We're up for our third presentation this afternoon. This is actually a nice block of time because the way the schedule worked, each speaker ended up with a half-hour block of time, and things are a little less rushed. So please feel free to think up your questions and ask your questions. There's plenty of time. Our next presentation is predicting surface coal mining in Appalachia. From Dr. Michael Strager. Dr. Strager is an associate professor for the Division of Resource Management in the School of Forestry and Natural Resources at West Virginia University. He's been applying GIS, remote sensing, and spatial analysis in his research and teaching for over 15 years. Prior to his current position in academia, he worked as a GIS analyst and water quality specialist for the Edgewater Technologies and spatial analytic consulting firms, and for the nonprofit Canaan Valley. I always mess that up. It's a nice resort. Canaan Valley Institute. He has graduate degrees from West Virginia University and an undergraduate degree from Penn State. So, with that, please welcome Dr. Strager.
Thanks, Mark. Okay, how's everybody doing? It's always tough to get in that early afternoon, 2 o'clock session, lunch thing setting in. I always get my worst student reviews at those 2 o'clock times in class. So I'll try to rally and be entertaining and good for you guys. Okay, so I'm going to talk about how I developed this spatially explicit coal mining predictive model. Now, it's spatially explicit because I'm looking at individual raster cells throughout the whole Appalachian region and combining that with some county-level model predictions. And I'll refer to that a couple more times as well. And you'll see how that spatial explicit part really pops out. So, not too much discussion about coal today, right? I haven't heard the word coal mentioned too much, and it's still part of our energy mix, right? It still is. It's a big part still of probably more of the southern Appalachians and around here, the southern coalfields of West Virginia and Kentucky. There's still a lot of permits that are being issued, a lot of permits still being evaluated. However, it is a much smaller part of our energy mix. That last little graphic down there below that text about how I think is amazing. How U.S. electricity from coal was 50% in 2007, and now all the way down to 37%. That's a big drop. And obviously a lot of things are impacting that. Oil and gas industry, competition, the price of coal, the different mix between steam coal and metallurgical coal, and its use, and government regulations as well also impact this. The uncertainty. Uncertainty is a big deal always with companies. So I want to give you an example today of how I applied these things together, and I'm kind of this really strange mix of a person. As Mark mentioned, I work in the natural resource forestry related field as part of my academic position. I've got this PhD in resource and environmental economics, a bunch of GIS experience and background and things like that. So if I had one project which kind of maybe pulls together all these things that I've done, it's probably this one in terms of the different GIS things, as well as integrating in some of the economic and the forecasting data. So economics is the science of trade-offs, and this is really kind of a trade-off analysis of spatial related data as well. Okay. So methods of mining, you probably all have seen this graph, maybe in a geology class you had, or a physical science text, maybe something like that. There's underground mining, there's surface mining techniques, and this kind of summarizes them on both sides there, different underground types, different surface mining method techniques. And so this study focuses mostly on surface mining. Now, surface mining is really 2/3 of our mining in Appalachia as compared to 1/3 with underground. So that's why it's kind of implied in a lot of numbers and figures and models that I'm going to show you. But this study focused primarily on surface mining. Now, these very large drag lines you see here, enormous. I should have had a picture of one of the scale related things if you've ever seen one of these. Just 5 years ago, there were 7 in operation in West Virginia, and they all moved out. We've only got 1 left, currently operating in West Virginia Southern Coalfields. So, big change in the times of what's happening. So, the goals of this study were to try to model this probability of future surface coal mining under all these different scenarios and things that are occurring, and to look at that kind of footprint on the ground and then allocate that footprint with some demand forecasts under different production scenarios through the year 2035 is what I was going to try to do with this study. So here's a flow chart. There's really divided into two parts. I think the main takeaway I want you guys to remember from this is there's a spatial model first in terms of predicting mining probability. That's this part up here, these guys, this section. And then after this, the second part came in, this future production data forecasting model to get this build-out scenario part. So this build-out scenario part, I think it can be applied, what the takeaway is to think about, applying some of these different types of ways to build out models. Don't just stop here with the probability surface. There's a lot of extra information you can add into together with this to create a particular build-out model scenario. Whether you're looking at oil and gas, whether you're looking at wind production, whether you're looking at land use conversion, there's a lot of different ways in the literature in which this is rapidly being used. I should also mention too, I have to be honest, I checked my phone after the last presentation, but I just got notification, this just got published too in the +1 journal, so there's a paper related to this too I can give you some information about later too if you're interested as well from this work. So we'll just do that just in that time in terms of going up and talking about it. Anyway, so the GIS data development, the summary predictor variables, academics always mention when they publish something, just so you know. This is a big deal. Anyway, so the data development, there's the physical properties type of predictor variables, and there's also these infrastructure predictor variables that were put together. So how we came up with these were basically from previous studies that tried to predict this type of surface mine or underground mining occurrence. So a lot of cold geology information. The sulfur content, ash, and BTU were things that we created as subsets off of some core data. So kind of goes across this fine line of how to use spatial data for using a model inside of another model. Kind of get some circular type of logic there, so that's not always the best thing. So I'm putting out some limitations of this as well. And we also have some infrastructure information regarding distances to power plants, intermodal facilities, distance to ports, and all railroads and population density as a negative factor as well. I'll talk about these in more detail as a part of the project development. Okay, so very large study area, as you can see, across Appalachian area, and I'll talk about these 9 predictor variables in a little bit more detail as well. Okay, the first one. Geological units. This is the one categorical data set we use in this model. This was reclassified under to general cold geology type. If you ever use geology, it goes across states. It doesn't always match up too well, right? Very difficult to sometimes find those correlation tables, get those things to match. This is a major undertaking to create these particular classes that you see here across this region, because we knew this is going to be a big factor in terms of predicting our mining extent. So this took quite a long time in terms of reclassifying, looking at lookup tables, talking with geologists, talking with Gene Kitts of Alpha Resources was really instrumental in helping with this. Another geologist, a hydrogeologist, the guy in Office of Surface Mining was really useful with this as well too. His name was Rick Manspeaker. He did a great job with this, helping us with this correlation table as well, getting this mapping right. Another big physical data set has inputs in this where the actual cold quality data sets. So this came from USGS, it's a cold quality data set of points. There were almost 3,200 points that were used as inputs. And the tricky part about this was using from those core samples the correct depth of that core sample, which would be used to basically capture that surface mining activity. So using a surface elevation layer, as well as those core samples, we had to select the proper depth that corresponds with surface mining to get ash, sulfur, ash, and BTU, and it's 3 additional variables from those. So the additional variables were computed using geostatistical techniques, specifically kriging. And kriging is a technique which uses both mathematical and statistical properties as part of the interpolation. It's not just like an inverse distance weight or a spline method, which is basically just a mathematical equation applied. It uses statistical properties as well as spatial autocorrelation, semi-variograms in terms of helping you with the improve that overall interpolation. So this is a sulfur content map. This looks like a categorical map, but it's really not. We have sulfur as a percentage. Our mapping unit is 1 kilometer grid cell sizes, so all these maps I'm showing you, everything was taken to a 1 kilometer grid cell size throughout this region. Okay, so that's sulfur content. This is ash yield, use that same approach with the geostatistical creating technique, and also BTU. So these were our coal quality inputs as part of this data set. On to the distance variables, we used not straight line distance, but we used a distance variable related to a network distance. So developing a network for all of our particular features we're interested in mapping distance to. In this case, this is an example for looking at coal-fired facilities in terms of power plants. We looked at that network distance on the left from those sites. And then since this was a spatial continuous model, we took those distance values from this network grid analysis and interpolated them with inverse distance weight, basically fill in these areas because we didn't want these to be no data or zero values for anything that wasn't on a particular road network because the spatial model was mapping this continuously throughout the region. So we took the network model interpolation, network distances, and interpolated that to create this map on the right, which shows those distances off essentially those road networks. So what you get is something that looks kind of like this. So there's a distance off of the road calculated in this, as well as the road network distance itself. So one of these variables we used were the distance to power plants. We had a total of 251 power plants throughout this region. That includes 25 new that are in the process of being built, believe it or not, and 92 that are slated for closure throughout this region. So that's our 251. The data source is from the Energy Information Administration, Source Watch, Department of Energy data set as well. So we had a study area. This is the Appalachian landscape cooperative extent. The extent of coal is inside of this, so obviously this whole area does not contain coal. You'll see further maps that just have a smaller subset within this, but this area is essentially our study area boundary extent. So in some cases, to capture some of these outside or boundary impacts from power plants, we went outside that boundary to obviously have a distance metric associated with it. That's why you see a lot of these points outside of that extent. Okay, so the next one was intermodal facilities. Intermodal facilities include rail, truck, river transfer points in which coal is taken to. Obviously not the air transport, but these are locations which it's important to have destinations close by where decrease obviously those production costs and decisions about where mining may occur if you have some shorter distances to these intermodal facilities, cutting down on costs. Inland ports, this is limited to ports handling coal and related commodities. Again, using that network distance as a distance metric variable for distance inland ports. Now, distance to railroad was one which did not use a network model. We used a straight line distance calculation for distance to railroads, and the reason is, it might be difficult to see in this graphic, but these are some permit boundaries in that pinkish color and the green as railroads. And what happens, this is a bigger graphic of this, what happens a lot of times is these little side spurs off of railroads were actually created in a lot of these hollows in different areas throughout the region to have easier access for getting that coal from the mountains to the rail system. So for railroads, since we had the intermodal locations also in there, we considered just a straight line distance to the railroad spurs and main locations throughout this region. So that's why this particular grid was a straight line distance model and not the network distance model. Okay, the one variable we also included too that was used as a predictor variable. We expected kind of an inverse or negative association with this variable in terms of overall model, and that was the population density. Obviously, you're not going to have surface mining occurring in highly populated areas, or at least you hope not. This was created from the 2010 U.S. Census using block group data. Okay. Areas were excluded from the future mining footprint. Obviously, there's places that are not going to be surface mined, and this includes urban developed land use areas. That should say 2011 land cover was the data source for that. Conservation lands are already under easements. Public, private lands, not private lands, but public land, state parks. national parks and so on, and mined out areas. A mined out area was defined as a location in which both that surface and underground permits existed, and it was assumed, even though there are a lot of instances where permits are added on to existing areas, we kept those as possible areas, but the extent for underground and surface existing in possibly the same location was considered a mined out location. So these were removed from the probability model. Okay, existing surface lines. So I just explained to you the independent variables. This was the dependent variable of the model for this random forest modeling approach to talk about a little bit. These were mines mapped from active surface mines, permits from individual states. And this took a long time to put together, you wouldn't think, but it was very difficult with some states getting this data all together. So there were some issues with some of the data sets, so we tried to standardize this as much as we could, and also we didn't want to have things that influence, or we don't have things influence our model that were maybe very different in the past, so we limited our active permits. We call active everything since 2000 on, so if no end date was listed. So our permit data sets from the different states look like this. This gives you an idea of the total active surface number of polygons, as well as the total active surface mine area. So with Kentucky, West Virginia up toward the top in terms of both number and surface area size. Ohio and Pennsylvania are also up there for numbers as well in that top tier. And Alabama, surprisingly to me, because I haven't really explored too much mining. I was very familiar with the mining in Pennsylvania, Kentucky, Virginia, and West Virginia from previous studies, but not too much in Alabama. That really surprised me in terms of the number of active permits there. And you see some differences, obviously, with the size of those permits as well, which was also kind of interesting. There wasn't always a one-to-one correlation or linear relationship between the number and the size of those permit areas. So this is what those look like. And again, so that was a dependent variable. Explanatory variables trying to predict this. And the model that we used is an ensemble tree method called random forest. And the random forest method, it's been used in a lot of recent studies that include this kind of machine learning approach. So the process, this is run in R, and so your output grids come from ArcGIS. They're used in R to basically run this thing, and for 1 kilometer cells throughout this region, you get this out-of-bag model performance, 87%, which is very good for this random forest model. They tend to overfit a little bit, so we were concerned about that. There's a system in which you go through which enables you to identify variable contributions. You can pull out some of those that aren't making much sense in terms of the overall model of contribution. And overall, the random forest model did very well based upon our test of this compared to some other methods we used. We also used the maximum entropy model we used, a weights of evidence approach, and also boosted regression trees, if you ever heard some of those techniques. But anyway, so we're happy with the random forest model output. This is a higher probability areas. You see here in the reddish color in terms of where that's predicting higher probable areas for surface mining to occur. And the literature says you can go down to about a 0.6, 0.65 in terms of what you're calling good probability from the random forest output. We're a little bit more conservative on this. We took our probability model map, which is this, and we said, well, let's only go down to 0.9. So if we only go down to 90% probability, those are the locations in which we're predicting where surface mining is going to occur. So that's our spatial model from this first part of this analysis. So I went through with just these predictor variables, known mine locations, statistical model to get this map future model probability. So then what we did was we integrated in this future coal production data. Okay, so we just didn't stop with this map by itself. It was kind of interesting in a way. We also wanted to say, well, okay, that's on the landscape where they might be, but what are some of these other economic factors? Because if you know anything about mining in this region, mining up here is much different than mining down here, and over in here. Okay? So fortunately, we were able to use a lot of information from this Energy Information Administration regional forecast. This is from 2013, and a lot of scenarios are put together for this. And what I learned about forecasting is if you're ever not sure about the future, but you want to sound like you know something about the future, come up with a lot of different scenarios, right? Anybody can predict the future. You got a ton of scenarios. So that's what they did. They came up with 28 different scenarios for predicting the future. We can all do pretty good if we had that many scenarios to think about. Well, if this, then this, and so on. So this is coal production by region, which I really like because it looked at coal production, surface, and underground. Now, I told you that I'm only looking at surface production in this model. So what we had to do was we had to convert to surface only. We computed that average percentage. We had county level information from this report too over the years past to basically break down that ratio. Okay, so we were able to take their total coal production and associate it to just surface production. So these are all the different scenarios they came up with, 28 different scenarios. And I could have used each of these different scenarios in this model. Okay? And it's possible to do that. It's not that bad at all. In fact, it's something we're exploring too. The two funding agencies for this. It's kind of an interesting project. Kind of got one on the side a little bit. So this was funded by both industry and also by the Nature Conservancy. You might have seen some of the other Nature Conservancy projects. That they had a shale gas prediction footprint. They also had a wind energy footprint that they did. So this is designed to actually complement those two. But the difference is that industry and the Nature Conservancy both contribute to this particular study. They're both very interested in it and so on. So as part of these production forecast scenarios, what we did was we used the reference case kind of as is, if everything kind of stays the same as best it can. Even though if you would have predicted what would happen to coal now, 5-10 years ago, that wouldn't have fit really good reference condition, right? We also used a low coal cost scenario. That's the case if coal is very inexpensive to produce, to capture, to get. Okay? So that would be a case in which coal production would be high. The other example is if coal production is going to be forecasted to be very low in the future, in which we have a regulatory policy of a very high greenhouse gas and low gas prices, which would mean more competition from gas. So we have three scenarios: an as-is, a situation where coal production is going to be very high, and an example where coal production is going to be very low, looking into the future. Okay. So again, this was based upon those scenarios exist for each of these 5 different regions throughout our Appalachian extent. So this is how they broke them out by county. Okay, so here are the reports coal forecast productions by region. And on this left axis, you can't see this too well, this is short tons, million of short tons of coal. So the axis varies between the regions, and you see the 2040 production scenario case out. So reference case, that's what we use in our models, low coal cost, and a greenhouse gas, essentially a regulatory scenario with low gas costs, which means more competition from oil and gas, low gas prices. So as you can see, my point in showing you these different ones were much different trends with whether you're looking at northern Appalachia, southern or the interior as part of how these things look looking into the future. So our challenge then was to say, well, how do we use these things as part of our probability model? So we have a probability map which each individual cell, 1 kilometer cell, has a value for in terms of probability. And like I showed you before, I only went down to that 90 percentile probability. Well, now I want to say, of those high probable cells, which ones are actually going to be used over different production ratios. So what I needed to do was to find this area on the ground, which is what my pixel cells are, and relate that to an amount of coal produced with area impact. So this was possible with a study that came out, Brian Lutz was the author, and he looked at West Virginia and Kentucky data, and he calculated surface mine area of these current permits and what was actually produced there. So once he had the total production from that data, you could divide that total production by the mine area, and the result is 80,000 short tons of production occurs for each 1 kilometer of surface mine disturbance per year. Okay, that was a very important part of the study, because without that, we couldn't then allocate the demand to our on-the-ground pixel cells in that probability map. Okay. So we took our probable areas and then allocated them to these regions based upon the different regions, northern, southern, central, southern, and eastern, in terms of those allocations. So in some cases, this 0.90 got completely used up in these regions. In some cases, it went below. Okay? We had to maybe dip down below 0.90, we had to maybe go down to 0.8 or 0.75 or something like that. So that kind of gave us some information in terms of how our spatial model was really doing based upon the economic forecast. Is it likely you're going to use up all those predicted areas? Is it likely in some cases you might have to go down to a 75% probability mapping on the surface to allocate that particular demand? In some cases, you could be pretty sure that, hey, if I'm only going down to like 0.9% probability, and that's probably pretty tight in terms of what that looks like in terms of demand to on-the-ground probability. Okay? So this is what the results look like. And I apologize, it's obviously tough to see at a scale this big, but there's two different scenarios run here in terms of this is the low coal production, and this is the high coal production scenario. So you definitely see more red allocated on this one as compared to this one. And so this gives you that spatially explicit footprint based upon the demand and also the probability from the landscape of where surface coal mining can possibly occur. Okay? So it's easy to show results like this, but when I'm reviewing papers or whatever, I always like to see, well, how good is this? Can you do any type of sensitivity analysis? Can you do any type of accuracy assessment? So how well did we do on this? Well, what we looked at was recent surface mine permits in West Virginia. We also had some data from Alabama. I'm going to show you this table. These were permits that were approved but not yet started yet. And we want to compare those with what our model results said. So this is just a map kind of overlaying those. This is the EPP permits. This is what we're excited is probability of 90% above. And where the surface permits kind of overlay on top of them. And this is a table which kind of summarizes that a little bit. So this is what this means. Let's look at Alabama first. So for the 86 permits, permit polygons from 2013, to allocate all of those 86 permits, we only had to go down to a 96.5 was the average probability score for allocating that future demand to. Okay, so that's pretty darn good. Feel pretty good about our model, or at least that estimate they're giving us for Alabama, and that demand as well. So the number of permits that intersected the high likelihood areas from the random forest score that were 90% above were 77. So 77 out of the 86 were at least a 90% probability or higher. That's pretty darn good. Okay. West Virginia, not as good. Our average random forest score for all the permit polygons was good in terms of 80%, obviously lower than 90, and then 26 out of 42 or 90% or higher. So one of the things we learned from this, well, maybe we shouldn't be as conservative as we are saying using a 90% probability. Maybe we should drop that down to an 80 or even something along that might be a better way to allocate some of those values across that. So this was interesting as well. And a couple points I want to make out before I go to my next slide here is that this is not I say spatially explicit, but it's spatially explicit across a region. This is not something you would want to use to go inside of a county and predict the spatial location within a county. The 1 kilometer cell size, don't feel it really supports that well. So it's not a site planning tool or a site expectation tool for saying mining is definitely going to occur in this part of the county, it's not going to occur in this part of the county. It's more of a regional type of model for those purposes, okay, of the overall perspective on that. So again, spatial model integrated with economic and regulatory scenarios is what the main thing I wanted you to take away from the study was. The key factors which really drove our model: coal geology type, sulfur content, coal BTU, and distance infrastructure, essentially in those orders. Again, not an individual mine site model. What you would need to do to create an individual mine site model is basically do what the mine inspectors do, or do what the mine planners do, which is go out, look at overburden, look at that core at a site, actually measure that coal thickness. Those very site-specific things that engineers do at a site. So we weren't doing any of that. We would love to have that coal thickness data or throughout the whole region. And I know in some places it does exist. In Pennsylvania it does exist in some places. West Virginia is getting better with this, especially in southern coal fields. But throughout our whole study area, we didn't have it consistently, and we didn't want to have one area have it and one not. So we are now looking at using the same approach, but more of an individual site model as well, down the road where we do have that information available. So it's focused on large regional extent to complement, again, those wind and shale gas models which were already completed. And I'll just read to you that last bullet since I wrote it. I was like, that sounds pretty good. So it's possible to develop this interlocking framework, voluntary practices, comprehensive planning, sensible regulation to ensure that extraction of this very highly desirable energy resource, coal, still evolves in a sustainable and equitable way. So I've been working on coal-related issues for a long time, mostly in the water quality area. And it's interesting to see how this transition is occurring from these additional impacts in terms of regulatory processes, price of coal, and competition from oil and gas is really changing this industry throughout the state and the region. So thanks for your attention, and good.
First question, is your next project going to predict deep mining? That'd be interesting to look at, especially from up here in southwestern Pennsylvania and Panhandle. We deal a tremendous amount of deep mines, and the mines are still expanding. Consul's expanding theirs, Alliance and Murray are expanding their mines. Can the same techniques be utilized to predict the future deep mining?
I think in some cases they can, other cases probably not so much. I mean, I think that it's just we really kind of, we backpedal a little bit on the whole mining thing by only looking at surface mining. Integrating in the underground mining just creates a lot more complexities, we thought, especially because of just how it's captured. I mean, once it's out of the ground, it might be the same thing as some of those distribution networks and things like that. But, so to answer your question, no, we really don't have any plans because we feel that's just going to be much, much more difficult than this approach was to the underground mining. Yeah, I think with underground mining, even at a smaller extent or study area, it still has a lot of complexities for it.
What still drives a lot of the deep mining is the export trade. A lot of the coal comes up, gets put on train, shipped to Baltimore, and gets sent to China. During the economic factors you were looking at for surface mining, was exports part of that economic model? Or is it just based totally on price?
Based totally on price, yeah. So that was kind of embedded in there as well. We took out that EIA report in terms of what was on that. Yes?
On the sensitivity, is this assuming that regulations will stay the same, or it's going to be more stringent?
Yeah, the as-is case, regulations stay the same. And then that greenhouse gas at $25, that would be obviously an increase in the regulatory requirements. Yeah, it's kind of interesting. I really like just, evaluating these, seeing how these things really differ across the region, and because there's a lot of big regional impacts from coal mining, price of coal, regulatory issues don't affect everybody the same. Coal is different. There's a lot of metallurgical coal still being mined. There's always going to be need for that. Always using coal for steel. Can't really substitute that too well. But for steam, there's obviously competition, oil and gas, and so on. And the need and regulatory requirements for cleaner burning coal as well. You look at some of those sulfur maps and where some of that sulfur location is. I thought that was interesting as well too. Just having, people, mining engineers and geologists obviously know these things, but you see these things spatial analysis where there's different demands and locations for resources out like that.
Any other questions?
Yes.
What was the paper, or what publication is your paper in that?
The +1 journal.
+1.
Yeah, +1. They said it'd be September this year, so. Like I said, the other two papers that were on predicting shale gas and predicting wind footprints were also in +1 too. Yes?
Were some of your surface variables, the infrastructure variables, weighted one more than another as a value, or is it all
They were all equal values as inputs into that probability model. Random forest basically uses similar to a classification regression tree that's run multiple times. It's used regression trees like that. So it's basically coming up with that variable importance on its own. There was no pre-weighting done. The data as it was collected or used was essentially input to that probability model.
What's the typical impact of surface mining in relation to surrounding infrastructures or constructions that may happen around?
Constructions in terms of,
For example, if you do underground mining, then you need to monitor for subsidence. Were there similar things that you would need to monitor if you were to build something around? or
Well,
near a surface
as
mine?
part of the permit process, you have to, surface mining, a lot of it's returning the surface mined area to original contour is one requirement, which is different obviously than the ground. They do have water quality standards as part of it that are applied with a permit, how you're going to treat discharge water potential. And within certain, there's iron, there's sulfates, there's pH as an output requirement from that. So a lot of the water quality things are similar, but the surface components in terms of original contour, what do you do with overlay and spoil, how you have water retention ponds and so on, that's all part of surface mine, which is a little different than
Good. Thank you.
With that, that concludes our first session of the afternoon. Our next break, we're on break now until a few minutes after 3. The PM break is sponsored by Cabot Oil and Gas, and we'd like to thank them for their sponsorship. And we'll see you back in here in a half hour. Thank you.